Hello and welcome to the Secure C and C++ Development Lecture Series for the Offensive Computer Security 2015 OpenCourseWare. My name is Owen Redwood and this is hosted at hackallthethings.com. So the audience intended for this lecture series is everyone from beginners to advanced C developers. The rationale is because you are likely taught wrong, and I can back that up. Back that up, we're going to start covering bugs in programming textbooks that have been there for decades. And there's some blog posts that are really good that highlight this exact topic, that scream that we were all taught wrong and betrayed by the C gurus. And, well, not all of them. Then we'll dive into the first lecture on the fundamentals, covering strings, pointers, integers. This next lecture we'll cover heap bugs, format strings, and race conditions, some of the harder security topics in C. And so, to start off, the code on the right is a vulnerability in programming pearls. It's a 1986 textbook. It wasn't caught for 20 plus years. It demonstrates a standard binary search. It's part of a library in Java, and it's 15, 16 lines of code, and it was actually formally proven correct with formal methods. And take some time right now to pause the video. I'll give you 15 seconds and see if you can find the vulnerability. So, the answer is that these are signed integers. And if low plus high are very large numbers, this will wrap around to a negative value. And ultimately, at the end, a negative number may be returned. And again, this is used to return a index in an array as a binary search for a value. And if you use a negative index to access an array, that can be unsafe, if not vulnerable, if used in certain settings. So the proper way to have this done would for these values to be unsigned integers, such that they cannot have negative values. It would wrap around instead to 0, and you could have length checks built into this to prevent even that. But I digress. There are other things that we were commonly taught wrong, using pound defines for max sizes. These again are by default signed integers. And so if you are comparing it to a possible signed integer to another signed integer, and this one has wrapped around to a negative value because it's gone up so high, then it will pass this check and perhaps do something unsafe. Using, again, a signed int I or signed int j for loop counters. These are signed integers that may wrap around if there's over 2 billion elements that you're searching through. Often you don't need a 32-bit or 32-bit variable to do for loops. You can sometimes do it in a byte or a short, but I digress. Another common practice I've seen in textbooks is examples with unsafe variable scoping. They'll declare a local variable and then they'll return the same thing. It gets essentially freed on the stack. The pointer to it that gets returned is still, can be used, but that memory space is not protected, and any subsequent function call can trash that stack frame. Then, when the 64-bit era came along to replace 32-bit computing, a lot of textbooks didn't, or curriculums didn't adapt to teach how to constrain variable types such that they will always be, regardless of the platform, the same amount of bits, the same amount of bytes. And so, depending on a compiler, an int may be 16 or 32 bits, long may be 32 or 64 bits, and so on. Another common one I see in a lot of programming classes is just allowing students to ignore compiler warnings or using permissive compiler flags. Maybe they have deadlines, the assignment's not that important, but it builds really, really bad habits. Um, the Heartbleed bug, which made news headlines, could have actually been caught with a strict compiler flag. But I digress. Um, and so another thing is not teaching kind of order of operations in terms of the C standard and how order may be undefined for some operators. The following operation may be 1 or 0 depending on the compiler because of this. And then it kind of delves into the I plus plus are kind of side effects in the standard, and their order isn't really addressed or defined. Another common practice is just including, importing every library, not necessarily just the bits and pieces that you actually need. And for attackers attacking such a target, it's just a rich environment for ROP gadgets, which is nice and neat. Another common mispractice is unsafe array use or unsafe string functions. Strcpy is actually quite unsafe. And also just general signedness issues, not teaching students about integer overflows for even bytes, cars, and etc. If you have car equal to 127 and you increment it, it will actually overflow, but the OS, the processor won't trap because it's how it's declared. So if you're skeptical still at this point, you may think that a compiler will catch it if you use the right flags, or your source code auditing tool will catch it as well. And that's all well and good, but if you don't understand the fundamentals, a fool with a tool is always still just a fool. You may catch whatever you can for now, but it's going to stagnate, and you're going to, in other words, fall behind to the ever-growing security game. It's a fast-paced moving field. And so let's dive into the C101 lecture. So for the rest of this talk, we're first going to cover important topics in processor architecture and the registers and how they work and what they're used for commonly. And then we're going to cover strings, pointers, and integer bugs. The von Neumann architecture is the one most people should be most familiar with. It is the predominant architecture of desktops, laptops, servers. It does not include mobile devices, smartphones, most of what is now growing to become the Internet of Things. This largely is a resurrection of the Harvard architecture. And I will get back to the difference between the von Neumann and the Harvard architecture in just a moment. So for x86, which is von Neumann architecture, there are a number of basic registers that are used for everything from counting to pointing to source index for a string to a destination index for a copy or a move. EAX is commonly used for an accumulator value, but also holds typically the return value from any given function right before it returns. EVX is also used as an accumulator, but often used for base calculations in regards to arrays and pointers into arrays of objects. ECX is commonly used as a counter. EDX is used as a data address pointer. ESI is, again, a source index, and EDI is a destination index for string operations. EIP is the most important register that you need to know about for the x86 architecture. It points always to the next instruction that is going to be executed by the processor, and it is the main target of modern binary exploitation. Is the main target of hackers. ESP and EBP are also very important for attackers and security people because they pertain to the stack. ESP is the stack pointer, in other words, the top of the stack, and EBP is the base pointer, the base of the stack, with respect to the current stack frame. And we'll dive into that more in later lectures. So a tool we'll be using that I want to give a lot of credit to is hosted at gcc.godbolt.org. It's a visual C and C++ compiler that on the left side of the screen will show you, you can type just any C code that you want and it will be compiling it in real time on the right, showing you the assembly instructions. It works for PowerPC, ARM, and x86. It allows you to colorize and correlate each line of C source to the corresponding lines of assembly, which is extremely useful for learning all this stuff. And it allows you to see, if you're interested, the differences between the compilers, notably Clang and GCC. So, the best book I can point you to for this material is Secure Coding in C and C++ by Robert Secord. It's from 2013. It's extremely well done. Some of the heap stuff and dynamic memory management isn't that well explained, so I take more time in my lectures, which is the next lecture, to cover that a little more slowly so everyone understands it. It's not required to understand the source material, but it's highly recommended, and I do cite from it in some occasional slides. So C, no matter how much you may hate it, is inescapable. You can't use a piece of technology, at least one that's connected to the internet, without touching something that's been written in C. Even other languages that are considered safe, like Python or Ruby or non-C languages like Java, their backends, their JIT engines, or their interpreter engines, as you may otherwise know them as, are actually written in C. The vast majority of languages borrow concepts and practices from C. It was designed by Dennis Ritchie at AT&T Labs. He won a Turing Award for it. He has had a profound impact on humanity with the invention of this language, as well as perhaps the kind of derivative invention of the security field because of all the problems that arise from using C. It's used in everything from operating systems to embedded systems, so you'll see it on planes, trains, satellites, boats, and etc. Inside a single computer, you'll see it in drivers, libraries, firmware, and other languages. In SCADA, you'll see it on PLCs in the form of C++ in some cases, and you cannot escape it. Therefore, as a security professional, you should know all of this stuff rather well. It really pays off. So we'll start off with the basic stuff, like strings. So we're going to cover string types, the unsafe and safe string functions, some common bugs and vulnerabilities, and how to do things properly in mitigations. And so, just to cover the fundamentals, a string in C is a sequence of characters up to and including the null character that terminates it. It's commonly just referred to as an array, to be pedantically correct. The length of a string is the length of the sequence up until and not counting the null character. So the number of elements in the array, not including the final element that terminates it. The size of a string is the number of bytes allocated to it. The size of the array is the number of bytes allocated to it. The count is the number of total elements including the final null terminating character. So size does not always equal length because it depends on the character size. So typically in most programming courses you are taught that a character is 1 byte. However, many students are not taught how to handle multiple character sets, and that's why UTF-8 and other character encodings exist. A single UTF-8 character may be 1 to 4 bytes. There are other character types, such as a wide character, which, depending on the platform, is either 2 or 4 bytes. And so strings can be normal, which is considered 1 byte characters. So a normal string is just regular characters, cars. A wide character string is characters, as I previously mentioned, are either 2 or 4 bytes wide each, or there may be string types that are theoretically made up of heterogeneous character types. I have yet to see those in any practice. So, do you know how to develop an application that can handle user input in all sorts of different languages? Korean, Chinese, Arabic, Russian, etc.? Because I don't, and I would bet that the majority of programmers do not either. And it's an incredibly boring topic, and I don't want to get into it further. And I just refer you to Wikipedia for further reading. And there are all sorts of character encodings, and this is a rather extensive list that one might have to be aware of when programming such an application, such as a web browser or operating system or etc. However, the handling of universal characters or various character sets is usually done at a single point, and this is the act of this is called character normalization, so that the user input all gets rendered into a normalized character set such that it is handled the same way throughout the internals of the application, and typically it is rendered back into the original character set when it is printed back or returned to the user after the computation is done. But I digress. That is all boring stuff. But it's still very relevant, even even to the point where it's the source of vulnerabilities and problems today. Just a few months ago, in 2015, there was a iOS bug for iPhones that was all over the news. The characters that you see on the right were in an SMS message that was being sent around the internet, mostly started via Twitter, that if it was opened on an iPhone, it would actually cause the thing to crash and reboot. It would make it physically power cycle. And it was just made up of a string of Chinese, Marathi, and Arabic characters, under 150 bytes. And users' only way to deal with it is to avoid the message, do roundabout things to get it to open up even the Messages app again, and it ultimately had to be patched by Apple. But this is rather profound that it made the device actually fail at such a deep level that it had to reboot from a single text message just because it handled the character sets wrong. That should make you think a lot of questions. But I digress. So, characters can be unsigned or signed. Simply the difference there is that a signed character, once it gets to 127, it's still 1 byte. Once it gets to 127, if you increment it further, it will wrap around. And that is typically undefined behavior. It depends on the compiler. It may not do that, actually. Anyways, characters by default, I believe, are signed. Strangely enough, the C standard decided to make a decision on whether or not characters should be signed or unsigned by default, like integers are just raw int is signed by default. And so for W cars, I think they are signed by default as well. I forget. Anyways, a W car wide character exists to support what is considered the largest extended character sets among the common supported locales, and that's in respect to most operating systems. Operating systems typically are released for regions, and so there's locales specified for regions: Europe, Asia, Middle East, Oceania, Americas, etc. And so that is why WCAR exists, and WCAR has its own family of string functions that we will cover. So, depending on the platform, a wide character for Windows is going to be 16 bits, and it's going to be UTF 16. But for Linux and OS X platforms, Apple platforms, it's going to be 4 bytes, 32 bits, UTF 32. And so, as I said earlier, the size of an array is the total number of bytes that it takes up. So if you use size of to determine the string length of a wide character array, you are doing it wrong. It's going to return a number that is at least double what the actual length is, which can cause buffer overflows and problems. So, string length is a function that is calculated at runtime. Size of is actually calculated at compile time. If you look at gcc.godbolt.org and play around with comparing the result of string length and size of, you'll see that instead of size of being called, there will just be a hard-coded number returned, and that's produced by the compiler itself. And for wide characters, there's WC string length, and it is quite common for developers to mistake these two functions, string length and size of. The following example, depending on your compiler, will illustrate this. We just have 3 strings, C string, signed C string, and unsigned C string. And it's a very, very simple function. It's just calculating the string length of each of them. For a signed string and an unsigned string of just car type, this is actually going to trigger compiler warnings. And so that may prompt a unknowing developer to switch to something that's going to calculate the size, or what they understand the size of the string to be, and in a manner that's not going to trigger such warnings. So from my testing with GCC version 4.2, this does not return any compiler warnings compared to the previous instance of using strlength for these signed and unsigned variants of strings. So that's an interesting nuance. Some compilers may act differently, though. So the following are a set of string functions. The majority of them are unsafe. Some of them are C standard, some of them are not. They're Windows functions. So that is a source for confusion among many developers, differentiating between Windows functions and C standard functions, especially when they have to develop something that is supposed to work in Windows, Linux, and OS X platforms. Any reliance on Windows-specific functions will fail to be multi-platform compatible. And so each one of these has their own different specifications on what parameters they take and how they are properly used. And the following are concatenation functions. They take string X and string Y and they stick them together. Strncat will do it more safely than strcat. In general, you are taught that the presence of an N It dictates how many characters to copy, and thus is more secure than just the blind um, stir functions that don't care about bounds and can cause buffer overflows. However, the end functions, the stern functions, actually aren't guaranteed to append a null character at the end. So there's no guarantee that it will result in a null terminated string, which means that if it's used in subsequent string functions, it may result in a buffer overflow. However, snprintf is a safe function that guarantees that it will be null terminated, and we'll talk about that more in a little bit. So there are a number of common errors that we're going to cover with regards to string handling. Unbounded string copies or improperly bounded string copies, off by one errors, string truncation, and other null termination errors. And these are all things that in the textbooks cause undefined behavior and potentially result in memory corruption. And security folk are always very interested in any bugs that result in memory corruption, as those are often the most common bugs that are exploitable by attackers and can have the most serious impact. The common culprits of buffer overflows that all C developers should be aware of are getS and strcpy. These have caused many historical problems. getS just cannot be used safely. Strcpy can be used safely when copying around static strings, but is commonly unsafe when handling any form of user input. Newer culprits of buffer overflows involve the misuse of strncpy, strcat, memmove, sprintf, strtoken, etc. Strncpy and strcat are taught by many as totally safe functions. In fact, you can probably find a dozen Stack Overflow blogs or threads talking about how these functions cannot cause security problems, which is demonstrably false because they do not guarantee null termination, require extra programmer calculation. Thus, if you pass it a max length string that doesn't have a null terminating character within that sequence, it will not null terminate it, and subsequent stir copies or string copy functions that occur afterwards will calculate the length wrong and potentially cause memory corruption. So they can be used unsafely, and sometimes the developers input the size wrong, and in other words, use it wrong. So getS simply keeps grabbing characters from user input until it reads a end of file character or null terminating character, which is pretty trivial to see how that can overflow a buffer and corrupt adjacent memory. Strcpy effectively does the same thing. It keeps reading from the input string until it reads a null terminating character, putting each subsequent character into the destination buffer, regardless of the bounds of that buffer. And so I've found a number of vulnerabilities that have used the safer version of strncpy, which again is, I don't consider purely safe because it doesn't guarantee null termination. Anyways, I found a number of vulnerabilities in the wild that just use this wrong. They are inputting the wrong parameter. It should be copying the length of the destination buffer, not using the length of the input string. Again, this is equivalent to the unsafe strcpy in its base form because it's doing it improperly. And this is actually quite common. sprintf is a safer function. It guarantees null termination, though snprintf is a bit better because it takes into account the size of the destination buffer. So this, again, would be unsafe. Um, so, so off by one errors are commonly overlooked by developers. They're similar to unbounded copies, but they're a little more subtle and harder to detect. They're commonly thought of as very hard, if not impossible, to exploit, which is usually wrong. Um, if you can overwrite just one byte of another variable in the stack, you can often have profound impact on the rest of the logic of that stack frame, of that function rather. Or if you can overwrite one byte of the return address, you can sometimes engage an entire ROP chain, or lead to a function that is a little more exploitable, or do something that, as I just say in general, furthers the development of the exploit. But I digress. So this code just demonstrates a very basic problem here. This for loop is just going to a hard-coded upper limit and is copying from S1, which is only 9 characters long. So this goes over by 1, copying into dest. It will copy the null terminating character and then 1 past it into the memory space of the destination. And the problem is that this will overflow on the heap, and that may cause problems when that chunk gets freed, or if there's a neighboring heap element, and so on. But we'll get into that later. We haven't really covered how the stack works, how the stack returns and everything kind of recurses, and how EIP is corrupted by stack-based exploitation. But we'll cover that in just a little bit. So, string truncation is another common error. However, this just happens when too large a string is safely put into too small of a destination. Simply the result is data is lost, and depending on the application logic, this may be a vulnerability, but it's quite rare for it to actually be an exploitable vulnerability. Again, I've said this a lot, null termination errors are very, very common. It just involves failing to properly null terminate strings. Certain safe functions don't actually null terminate. If there's not a null terminating character within the first n bytes, there will be no guarantee that the destination string will be null terminated. So to mitigate these, it's best to use to follow the best encoding practices. If you do have to work with multiple character sets, this is a pretty good guide for character transformations. And then there's also compiler flags that will help you determine which functions are safe to use, and you can use a single unified model for handling strings. And there's other flags like fortify source, and stack protector is typically on by default nowadays. And that brings us to pointers. So we're going to cover the fundamentals of how to use pointers. We're going to cover function pointers, which are the most interesting case when they go wrong. Data, we'll cover errors with handling data pointers. We'll cover the global offset table and the detour section. The global offset table is unique to Linux, but it's worth covering. So, a refresher on pointer operators. We're going to cover the asterisk and the ampersand operators. When used as a declaration operator, the asterisk operator denotes a pointer to an object of the given type. So car star x points to either a single character or an array of characters, similar for int star x, z, and so on. When used as a unary operator, not in a declaration statement, it will dereference the variable. It will, at the assembly level, it will load the address given by the pointer and store the value at that address, into a register. For a function pointer, it will call the function given at the address stored in the pointer, and it will then load, typically depending on how the calling standard works, the result of that function into a register, say EAX or RAX or etc. It is commonly understood that a dereference of a null pointer will typically trigger a segfault, as the null page or the address of all zeros is usually memory protected and part of what is typically kernel space in most processes on most platforms. However, I should note that many modern embedded systems allow you to map memory at the null page. So if you have some form of code execution capabilities on an embedded system and you're able to map the null page, it is often a means of privilege escalation to find a null deref vulnerability and trigger it, hopefully in a manner that calls a function pointer. But I digress. There are multiple ways to exploit null pointer dereferences, but it just really, really depends on the situation. So this is a very basic model for understanding the relationship between a pointer and the dereference operator of a pointer. The pointer itself, when you just print it out, will just show the address of the target. When you dereference it, it will show you the value of the target, if it's just a data pointer. And the ampersand operator shows you the address of. So ampersand x will show you the address of x, of the pointer itself. Not the address of the target or anything in regards to the target, just the address of the pointer. Very simple stuff. It kind of works in a forward progression. Anyways, so the member of operator, this arrow combination, is used for dereferencing structures and accessing a member of that structure or a function of that structure. And how that works is it takes the base address of the structure and adds however far into it that variable is the offset to get to there. So this is essentially the equivalent to array indexing. However, structures may have different types. So this would be, int, and then char, which is typically 1 byte, as opposed to integers, which may be 16 or 32. But I digress. So just to cover array indexing, it's going to return if this is x sub y, it's going to return the yth element as an offset from the base address given by the pointer x. And is exactly equivalent to dereferencing the base address given by x plus the offset given by y. Now, that may depend on the object size. Obviously, this would only be valid for bytes and chars, characters. So, for member of operation, it would be roughly equivalent to the base address given by D plus the size of each object in the struct x, y before the given target member variable, so name, and it's pretty straightforward. So function pointers, when they get executed, it's typically at the assembly level via call, jump, maybe a ret instruction, and the fun fact about von Neumann architecture is that it cannot distinguish between data and instructions. Fundamentally, that is originally meant to be a design feature, but now many von Neumann architecture implementations have re-engineered many features to correct that now considered design flaw. Conversely, the Harvard architecture has completely separate memory, physical memory for instructions, and a separate physical memory for data. And the EIP, essentially the instruction pointer, cannot ever point to the data part of memory. It is not allowed in the architecture. However, in most desktop and server computing, which is von Neumann architecture dominated, if you manage to convince the instruction pointer to point to some malicious data, it will execute it without any regard. So function pointers have to be handled carefully. If they are overwritten and then the function is called somehow, that can lead to malicious consequences. So, the following code calls the function here, good function, twice, but in two different ways. The first call here is done with a function pointer, func pointer that we have here, assigned to the address of good function. And we call it with this notation, and this corresponds to the following assembly written here in blue, that it loads the address of func pointer into the RAX register and then moves a pointer to the first parameter in EDI, and then it calls the function by using RAX. The other, perhaps more common way to call the function here is denoted by simply moving the function parameter into EDI and then just calling directly good function. Both of these operate in almost exactly the same amount of time, same performance, etc. This just runs the danger of you have to protect this variable. It is very sensitive to overflows and corruption. Now let's take a break and see if you can put to use what you've learned so far. In the following lines of code, there's a vulnerability. See if you can pause a video and find it within 60 seconds. So if you guessed the size of function here, you'd be right. This is an effort to clear the memory at the variable dest, which seems to be some matrix given by max chords of 5 by 5 of a real value, however big real is. Now, the problem of using size of here is that it's going to return the size of the pointer. Depending on the platform, it's either going to be 32 or 64 bits that are only set to 0. And that is going to cause problems when you expect this to be instead completely zeroed out. It may lead to use of uninitialized or improperly sanitized memory. And to give credit where it's due, this bug was provided by PVS Studio, which is a C++ code analyzer, and it was found in a Windows XP operating system clone. So this was a OS bug. I don't know if it actually ever had a exploit developed for it, though. But I digress. Next, we're going to cover the global offset table, and Windows and Linux use a similar technique for linking and transferring control to a library function when it's called from within the binary, whether it's a portable executable or executable ELF format. The thing to note is that the way Windows does it is safe. However, Linux's version of this technique is exploitable. And the reason is that the GOT, the global offset table, holds absolute addresses only, and it's stored at a static location typically, even with ASLR on. Only with full rel row in full ASLR is it actually loaded in at a different location every time the binary is run. But I digress. Now, what this does is when you first call a function, say like snprintf or printf or connect, it's going to go to the global offset table. The global offset table is going to have a loader function pointed to instead that is going to find the address of the desired function, put it in the place where it's supposed to be in the global offset table, and then call it. It's essentially like a hook, and we're going to cover hooking when we get to rootkit design later on in a couple lectures. But I digress. So every single library function used by a program has a got function. If it's a function that's inside the program itself, not in a third-party library, it's not going to be here. Anyways, so the function to load in the real address of the desired function in the library is called the runtime linker, and so this gets past control. It finds the function's real address and inserts it into the GOT. And then the next time you call the function, it goes to the GOT, and the GOT points directly to the function, and it doesn't involve the runtime linker again. But the way it is designed is, again, this is in a static location, the global offset table. So it has pointers to all sorts of fun functions, such as perhaps system or exec, that attackers might desire to call if they manage to hijack execution. So they can typically write to this section of memory because RTL has to be able to modify it. Therefore, it is not write protected. It has write permissions enabled. So if an attacker has the ability to overwrite just a couple or maybe a full pointer's worth of memory at an arbitrary location, a common technique is to overwrite a function that's in the GOT because it's stored at a predictable address and it has functions that are going to be called perhaps later on. This is a rather effective and reliable technique for attackers to gain remote code execution on a target system. And you can learn more with object dump given any arbitrary binary in Linux. However, we're going to revisit this technique hands-on in the exploit development lectures. So the detour section is also an interesting target for attackers. And it is only present with binaries compiled by the GCC compiler. I think also Clang? Not sure. But it's not going to be present in every single binary. It depends on the compiler. I digress. It also contains function pointers that specifically pertain to destructors for objects and classes. And it is also writable by default, which is interesting. The CTORs aren't really an interesting target because they happen before main is invoked. But if you manage to find them, they have all sorts of info leaks because they touch a lot of different objects and a lot of different parts of a binary. I digress. So the detours is something that's going to get called at the end of the binary's life cycle, or at the end of a scope of a function that uses and declares an object. And it might be a similar, it might be an effective technique in alternative to GOT exploitation and overriding to hijacking the instruction pointer by overriding function pointers. So, here's another example that we can use for a break in the lecture. Pause the video and take 60 seconds to see if you can find the vulnerability in the following code that was found in OpenSSL. So, the vulnerability here is that handshake func is just called as a function pointer, but it's not being dereferenced with parentheses as a function should be. So this is simply checking if the address of the handshake function is 0, then handle the SSL error, instead of checking the result of the handshake function. So this was an actual bug, a vulnerability found in production as OpenSSL code. It was found by PVS Studio, to give them the credit, and this effectively meant that it was not checking SSL handshakes, which is hilarious. Here's another bug to pass the time. See if you can pause the video and spot it within 60 seconds. So this is a classic case of copy-pasted code. Now, here, in the first function, it checks if the subnet is not equal to null. But if it is null, it then calls this alternative function complaining that subnet is not found. However, it seems like there's been some leftover from the developer's copy pasta, and it seems that despite not having a corresponding reference in the format string, it is still being passed as an argument. And so the debug printf, if it's like any variadic function, will still call this. This actually will be called before, to correct. This will be called before debug printf, and the results will be passed on the stack. But if subnet is null, this is going to be perhaps a vulnerability if an attacker can populate the null page, and perhaps use this as, say, a privilege escalation or some other form of exploitation. If they can populate the null page with shellcode, say just a huge NOP sled, and it will jump to the offset pointed by name, that's going to contain a function pointer. It's going to have to point to the NOP sled, and then the instruction pointer will obviously be hijacked and pointing to malicious code. I digress. Here's the final pointer bug. Pause the video, see if you can find it in 60 seconds. So what's happening here is that this is obviously a function that is overloading the operator of decrement. It tries to declare a temporary variable, and there may be some error, and this may have been intended to be TMP, but the bug here that's actually a vulnerability is that it is returning a reference to a local variable. This will get trashed right when return gets called. So it'll exist within the stack frame of this function, but once this returns, that is no longer protected. And so any subsequent function calls can totally overwrite this pointer and have it point to something else. And that is the potential vulnerability in itself. So, and that wraps it up for pointer security and pointer bugs. We'll now transition to integer security. So we're going to cover a number of topics here. We're going to cover bugs regarding the mix of signed and unsigned variables, integer truncation, integer overflow, underflow, other nuances, the rules for integer conversion and promotion, and other casting errors. So, here is for a single byte, because I didn't want to map out for an int, which would be 32 bits. Here we only have 8 bits, which makes it easier. For a signed car, it ranges from 1 to 127. from -1 to 128. Obviously, there's a 0, right? For unsigned car, it ranges from 0 to 255, which is, all ones in a byte. Pretty simple stuff. What happens when this wraps around to 1 in the most significant bit? If you add 1, if you increment 127, it is going to wrap around to -128. You can test that in the calculator. And the key point here is that with any signed variable, if it's used to keep track of a variable's or an object's size or length, it is going to eventually be problematic, perhaps even a vulnerability, if that number or object is too high or large. All lengths should be unsigned. Anyways, integer truncation is incredibly simple. I'm going to demonstrate it with a short example. If we have an integer I that's -1, it's going to be signed int. So it's going to be all ones. And we store it as a short. It's going to truncate. And so a short is going to be 16 bits as opposed to the 32-bit int. And that is at the assembly level. If we have I loaded into EAX, then X would simply be AX for what part of that it would retrieve. So half of it would be lost. In other words, half of it, the more significant half, would be truncated off. So this is some output from gcc.godbolt.org. And here we can see that the AX variable is indeed being used to move the part of RAX that is storing -1, and that is how it works. So obviously when you use a car or a byte, it's going to use the AL, BL, CL, etc. representations of that register, and for shorts, it's going to use the AX, BX, CX, etc. EAX is the 32-bit. RAX, RBX, RCX is the 64-bit version of the register, and in order to get the more significant half, it is simply a matter of bit shifting. There aren't registers that specifically exist for obtaining these, as it is all just a matter of either bit shifting it down or zoring out the AX or whatever you actually wish to do. There is a upper half for the 16 through 8th bit, and that's the AH, BH, CH, DH, etc. registers, and so on. So this plays more of a role in crypto systems and any form of hash calculation or integrity verification calculations like CRC checks, etc. Especially when they're designed to work on 32-bit and 64-bit platforms, especially across multiple operating systems. Variables should be declared with explicit type constraints, or rather size constraints. And the main example is that long variables differ in size on 32-bit and 64-bit systems depending on the OS, and it's not a standard across all implementations. And furthermore, it's pretty common to see the following example. On some 64-bit platforms, size of returns a 64-bit value, and typecasting it down to an int will actually truncate the most significant half off, which can lead to a completely incorrect calculation of something's size. The solution is to cast whatever it is as size t, as that is safe approach that is compatible on most platforms. So, to dive into the difference between platforms, there's four different models. Um, the LP64, the ILP64, the SILP64, the LLP64, and I do not expect anyone to remember this all. Here is a better slide that breaks it all down. This is, I think, from MSDN's reference site. And ILP32 is the data model for 32-bit systems, and it was consistent across Microsoft Windows, almost all Unix and Unix-like systems, and it changed with 64-bit systems. So it spawned three different models. The LP64 is for most Unix and Unix-like systems, including Linux, BSD, Solaris, OS X. LLP64 is solely the implementation of Microsoft Windows systems. And the ILP64 is for Solaris, Spark, and HAL computer systems. Very rare, not really worth remembering. But the difference is really we want to focus on between LP64 and LLP64. Obviously, long is different. Long is still 32 bits on Windows systems. Long is 64-bit on them. But long will differ between Linux and Windows, which is one of the key things to audit for if you're code auditing something that is supposed to work on both Windows and Linux systems. That is a dead giveaway if you find just regular longs used in any critical computation. So here are some safe type definitions. Pointer diff underscore t is actually a signed integer type that results from subtracting two pointers. So it's either the positive or negative offset from a given pointer to another address in memory. Size underscore t is perhaps the most well known. It's unsigned integer, so 32 bits, and it's the common result of a size of operator. It may vary in different implementations. I'm not 100% sure there. Then for defining integers or defining variables with predefined width, int 32 underscore t and uint 32 underscore t, and this whole family of variables where it's variable 32 or 64 underscore t is the correct way to do things in terms of constraining the width of the object size, and so on. So this is kind of a note for exploit development. If you're doing a heap spray, the size of a struct may actually change from platform to platform, and the thing about it would be the long here would either be 32 bits or 64 bits depending on the platform, and that might affect the chunk that it gets allocated to, whether it's like 32 or 64 or etc. And we're going to cover dynamic memory management and heap management in the next lecture. So keep this in mind. So the next important thing is covering integer overflow. What happens when you take a integer that is the max value and increment it? Well, the C99 standard dictates that the result is always modulo and it can never overflow. By that it means never overflow into adjacent memory. It will wrap around. So if you take an unsigned integer that is the max value and increment it, it will wrap around to 0. Just like this on the right. This is exactly what will happen. It will just wrap around all to 0. And congratulations, you've got a brand new car. Just kidding. So what about signed operands? It's actually in the standard regarded as undefined behavior, but it has actual implementations in some compilers. And there's an interesting blog post that I refer you to. I think it's Embedded in Academia has a good series on integer bugs. Um, so for non-C standard environments, the effect of taking a max value and incrementing it will, instead of a wraparound occur, will result in a saturation. And this occurs in graphics cards and digital signal processors. Um, the max value is just always returned. The max or the min will just saturate and stick there. It still does not overflow into adjacent memory. Um, and it's just an interesting case. So integer underflow simply occurs when you decrement the minimum value for a integer type or a numerical type. Um, so the C99 standard dictates that the result is always modulo. So if you have an unsigned integer 0 and you subtract 1, it's going to be the max integer, max unsigned integer. And for signed operands, this is undefined. It's kind of a more interesting case. What happens if you wrap around the maximum negative value like this? It's supposed to be undefined behavior, but it may actually be implemented in some compilers. Other nuances to cover, bit shifting integers is something that is forbidden if the target is a negative integer, because the most significant bit denotes the signedness when it's a signed integer. It is typically considered an error to shift a 1 into the signed position of a signed integer, and it's also an error to shift the bit shift by a amount or a number greater than the width of that object. So int is 32 bits on most systems. Bit shifting an int by 33 bits would completely clear it. It sometimes raises flags. And so coming back to integer truncation in this, if something is bit shifting a long by 32, that might break on Windows systems. Just saying. Another nuance is any number starting with a 0 actually results in a octal number. So this would be octal, this would be octal, this would be octal, and so on. And that trips up a lot of developers and can lead to miscalculations sometimes. So, what happens when you compare a signed integer to an unsigned integer in the same comparison, like this one? The result is that the unsigned version always wins. It will get promoted. Everything in that order of operations will get promoted to unsigned. However, there are some interesting cases to consider with regards to order of operations versus how the promotion works. Here, if x and y are signed, they will be added together as signed values before this comparison happens and the promotion then of this result to an unsigned. So, that is interesting. If either one is so large that they have a most significant bit set to 1, they will then be negative. So one of these will then subtract from the other, or in other words, decrement, which may lead to an incorrect calculation. So that would still perhaps be an incorrect calculation. And now here, the unsigned value of 1 is added to the signed value of y, then is compared to the signed value of x. This will all get promoted to unsigned because it's all the same level of order of operation, and that should be pretty straightforward. Now here we have the signed value of x and y are added, then they're shifted left 16, and here is compared to a unsigned value z, pardon the notation, this is the only slide that this is used on, and this will all evaluate as a signed variable before being type promoted to unsigned to evaluate to compare against the variable z. So this could have most significant bits set to 1 and then be bit shifted out, and that can lead to some interesting data loss and be possibly incorrect. So another rule for integer promotion or conversion is that whenever you're comparing multiple sizes, here 17 will by default be integer, everything is going to get promoted up to the maximum value. So the short here will get actually promoted up to int, regardless of whatever the developer intended, and so on. So, I think modulo negative numbers is not allowed. It should be a compiler error, but if that actually ends up in a variable, that would be interesting. And these are other things you can pause and ponder. So to wrap things up, there's something one of my friends, Sean, he found. There's, for no good reason, a signed size t. And the rationale for size t is that sizes should never be negative. But some people, for no good reason, wanted size t to return -1 for some reason. And thus size t was born. And so if someone fat thumbs the S key and types S size t instead of size t, you can get edge cases where -1 will be returned, and that can be very dangerous in array accessing, as well as malloc-ing and strcopies and etc., string copies. So integer bugs are incredibly important. They often enable other vulnerabilities that are dormant in the code and are left unfound. They're surprisingly common in crypto libraries, according to the Embedded in Academia blog post here. I wouldn't be surprised if there are integer vulnerabilities in Bitcoin and cryptocurrency libraries, at least to mine them, if not to check signatures or some of the wallet functions. They're often not understood well by developers and lead to vulnerabilities. There's a paper here that I've linked that's pretty good reading on catching integer bugs from code auditing perspective. And another topic I'm going to cover before we wrap this up is floats. Floats have precision problems. It's pretty well known for most developers, but they can also be a special value that is not a number. And this not a number value defies most Boolean comparison and other logic. And when it compared to itself, if you're checking for a float to be not a number, it will actually always be false. And you can read more about float precision and bugs here at the floatingpointgui.de site. Here's a quick bug. It should take 30 seconds at most. Try and find it. So it's only 4 lines of code. This would be an octal number. It was found in Chromium. It's obviously not a vulnerability, but it would just lead to something being displayed wrong. Now, here are some resources you can refer to for size rules. This is where the table came from for the ILP and LLP models. For motion rules, you can read about on this link. Floats and crypto libraries you can read up on. For crypto library bugs, Embedded in Academia has an awesome analysis. The blog author found vulnerabilities in, I think, 8 out of 9 open source crypto libraries that he found, where they were relying on totally undefined behavior in the C-spec to perform calculations, if not just bit shifting things wrong by greater than the max bit width and stuff like that, which is concerning because crypto libraries should be 100% solid, right? And that concludes this lecture video. Next time we will resume with heap bugs, format strings, and race conditions. Thank you.